Right, we're going to complete our segment on electricity by talking about the voltaic or galvanic cell, involving a salt bridge. All right, this setup is known as the Daniel cell. Some guy named something Daniel kind of invented it, so there you go. That's the cell. Okay, the Daniel cell basically has two beakers of solutions, different solutions. Okay. And you have electrodes on one of each beaker, and these electrodes are made of different things. All right. I'm going to use both reactive metals in this case, and it's connected by a wire, usually copper, and in the middle you have a voltmeter, which will take readings of the electrons that's passing through, and the output of those readings on your screen will be in volts. All right? And you have a salt bridge. Now, the salt bridge is also very important. So, what's going to happen is that the more reactive metal, or whatever in this case, will start the reaction. And I'm going to put specific metals and label this illustration properly now, because I want to use a specific example to kind of explain this concept. I think it's just a little better if I use a specific example. So here I'm going to have a zinc electrode, okay? And in the solution, I'm going to have a zinc solution. All right? In the zinc solution, there's lots of Zn2+. All right? So what it's going to, and on the other side, I'm going to have a copper electrode. And this will be a copper solution. And you have a lot of copper ions in there. And the salt bridge, I'm going to have salt that is very good and does not precipitate or does not react with any of the things down here. And it's just a very good salt, an electrolyte that dissociates completely. Very good candidates are potassium nitrates, because nitrates usually does not dissolve. There are also examples of sulfates, group 1 metals like potassium, sodium are good candidates. Ammonium is also a good, ammonium nitrate is also a good example. Whatever, there's lots of other examples. Okay, so what's going to happen? Here, the zinc metal is going to lose itself into the solution to form zinc ions. As it does that, it's releasing electrons, and the electrons are moving this way. So this means that the N terminal should kind of be here, if you want to consider it that way. And also, because this is the N terminal, and this is where the, I guess, spontaneous reaction happens, this will be the anode. Okay? Electrons are going to go through here, and it's going to get read by the voltmeter, and you're going to get a volt reading, okay, of some sort, and the electrons are going to come down to the other electrode, the copper electrode, and you're going to get stacking of copper, stacking of electrons in that copper electrode. And what's going to happen at this other end is that this is going to be known as the positive terminal now, because electrons are getting received in here. And so the copper ions in the solution is going to get attracted to the electrons on the electrodes here, okay? And you're going to get a layer of copper that's going to be plated onto the existing copper electrode. So as this is happening, you have to imagine what's happening in the solutions. So in the solution, the zinc metal is being liberated as zinc ions in the solution. So this whole solution becomes more and more positive because of the excess amount of zinc ions. All right? On the other end, you have the copper solution. The copper 2+ is being plated onto the electrodes. So what is going to happen is that this solution is becoming more negative because you're removing the plus, and whatever you have that is the anion. So for example, if this is a copper sulfate solution, what you're going to happen is that the copper is going to get plated to the copper ion is going to get plated to the copper electrode, and what you're left with is the sulfate. So this whole solution is going to become more negative. All right? And what's going to happen? The migration of ions will start happening. So this negative ions, the negative ions on this side, is going to move up through the salt bridge to the other side and get attracted to the anode. Whereas the positive ions on this end is going to move up the salt bridge to the other side, and it's going to get attracted to the cathode. Oh, so there you go, that's the cathode. All right, and on the salt bridge, you have cotton buds that stay soaked. All right, cotton buds that stay soaked. So there you go. You just have to remember that this here, you undergo oxidation because you're losing electrons, and here you're gaining electrons because copper 2 plus becomes copper that gets plated on the electrode. So here is where you can undergo reduction, right? And the salt bridge acts as a regulator of ions as the positive ions from the more positive solution migrates through the salt bridge because it's attracted to the cathode, and the negative ions on this other end of the solution gets moves or migrates through the salt bridge because it is attracted to the anode.